Hi, this is Pete Ekman with the RoboZone podcast. This is our Kettering GoPro Corner update. This is part Deux, part 2. I used the Deux because that was a reference to a movie back in the day. Hot Shots Part Deux or something like that.
Nice.
I always like it.
Funny that a guy with a German last name like Ekman. You know what Ek is in German?
No.
Real.
Yep.
Echt
I'm the real.
Things that are real.
Oh, the man, like real
Ekman.
man, like Ekman. I didn't know that. Now I know it. Thanks, Andy. I'm going to
telling
use
you.
that
You are
from
the
now
real
on.
man.
Yes, I'm going to use that. I'll use that in my wedding vows here in a couple weeks. She's laughing behind me. It's going to work. Thanks, Andy.
No problem, man.
So Andy, well, first, this is the GoPro Corner, but we're really wrapping this around a presentation that we started last week. This is part 2. John, how are you?
I'm doing great. I hope you had a great Mother's Day and everything that goes along with that.
Did a lot of stuff for my mom. It was good.
And I want to thank you on YouTube. I've saw it out there and everything. So I appreciate that. And we just got to push some more people looking at it, and we'll work on that.
We're going to work on that.
But I really appreciate that, and it looked cool.
So Andy, with that, welcome back. This is part 2.
Thanks.
You kind of blew my mind on the last one, so I have high expectations for this one.
Yeah, absolutely. I want 2 disclaimers again at the beginning. One, I am not an expert at this. I'm just somebody that John roped into talking, and I happen to be plausible. So I really think we should call this. Segment "What Andy Thinks He Knows." Okay. So if anybody finds out that I just said something wrong or I used the wrong word or whatever, just go with it. And you're probably right. But I think we can put this into a package where we land the plane today and talk about some of the underpinnings of how these neural networks come to the conclusions that they come to. And then you'll get a sense for how they get trained.
And at the end, remind me, Pete, I've got a couple pieces of cool good news.
Oh, I already know. I read it.
I got other good news too. Okay, but what were you saying, Henry? Wait a second. I think Henry has something to say.
Andy, John, you know, this concept of artificial intelligence has me going in loops. Smell that? That's my circuits are smoking. I will sing you a little song so you understand how I feel. After that, please explain this to me. I mean, hey, I could use some of that stuff. And I'm sure John could too. Ha ha ha.
Ha ha ha.
Oh. Gotta get the whole effect.
He gets his cheeks get red when he
He's
sings.
a little nervous.
Now I'm the king of the robots, a digital VIP. I've reached the top and I've had to stop, and that's what's glitching me. I want to be a man, a real one, and stroll right into town and be just like the other man. I'm tired of standing around. Oops, I want to be like you. I want to walk like you, talk like you too. And you'll see it's true. A machine like me can learn to be human too.
Nice.
So, Andy, how do we get him to be more human?
Well, so let's start by reminding ourselves where we left off last time. Last time we talked about regular engineering, regular old engineering. Oh, the host has disabled my participant
This
screen
happened last time.
sharing.
Yeah.
Participant.
You catch up on that now. I'll make sure it gets done.
So where we left our heroes was that engineers go to school to observe systems, think about how math can describe them, come up with a model for those systems, and then they can program the systems to seem smart, right? And then we knew from last time that they could also put a bunch of decision trees that they come up with into how a robot thinks, right? And it can respond to inputs and outputs and look like it's making good decisions, right?
You should be good, Andy.
That's traditional engineering. Are we ready to do sharing?
Yes, sir. You should be able to share.
Okay. So let's put a fine point on that. Let me come over to my presentation. There it is. And let's go back to the beginning of it. So what happens when you start singing at the beginning of these things? Oh, I did want to take one other step back. I have a music degree, you know, that is distracting, that singing robot bit. Okay, I liked it. But remember, smart things are everywhere. That's the AI. We wanted to talk about neural networks and why they're magical, right? That's what we're doing. So that's why we start with what it isn't, right? If you see that your robot gets this image that comes into it, then the traditional thing that I would do is I would say, oh, though there's a red background, I might look for red. I might take the red out so it becomes black or white, right? And then I'm only left with the white things that are left. And then I would say, where are those squares, right? Or where are the edges of those squares? And I could figure out the center of the square. And then I would know by the size of the square, how far my robot is away from it. And I use a whole bunch of geometry to shoot a ball, which I had also looked at the math behind it to go through this. So I'd have a model for the ball getting shot out. I'd have a model for how far away I am. And it would all be based on the math that I had thought of because I am a smart engineer, right? Engineer's smart, robot looks smart because the engineer, right, she programs it right. Okay, that's traditional. All right, now, neural networks are different than that. They work a little bit more like the human brain does. I was just thinking about this. I was outside and I heard a train go through Flint. There's a big factory and a train goes through and you hear the train whistle and immediately what do you think of? A train. You can't see the train, but you know that that big train whistle, right, has a very distinctive sound. And there's a bunch of neurons in my head that go, oh, that's a train. So there's a symbol for train in here based on what came in my audio cortex.
So I've been trained on that.
It shouldn't, yeah, that's good. That's good, John. I hadn't thought about that. So how does that work in human brains? Well, we have inputs that go into neurons, and those neurons are connected together in cortex. We called that, we talked about this last time, so I won't go into it. Great book to read is On Intelligence, which talks about the fact that auditory cortex and visual cortex and memory cortex, it's all the same structure. It's these layers of neurons, layers on top of layers, and they're all interconnected to each other. There's trillions of neurons, right? And some of them when they get an input, right, and they light up, then they get reinforcement because that was the right thing, like that train whistle. I've heard it and seen a train. So that those neurons that are about trains start to associate and light up and get more activated the more that I hear trains and see them and see they're connected to each other. And so all of a sudden you get these branchings of neurons that light up in parts of your brain when you hear or see things, right? So I know that's you, John, because I can see you and I have a symbol in here that goes, that's John, right? So how does that work with a computer though? Computers are really good at doing computation. And so we're gonna take a look at how data propagates through an artificial neural network where we're using math constructs to be the neurons. And we're also using now these sort of basic math functions to connect the neurons together, activate them, and figure out what's important. And by the way, of course, to get outputs. I don't know, can you guys see this part of my screen? Does that show up?
No, I'm only seeing the presentation.
All you see is the presentation. Great, good to know. Okay, so let's talk a little bit about that. So what do we need for neural networks to work for classification tasks? Now, what is classification? Classification is if I'm trying to figure out if that's a robot, or if you're John, or if this is a table, or if it's not. Is it something or is it not something?
Yes, no.
Yes, no, exactly. I'm classifying. Is it in that class? Is it not in that class? And you can use neural networks to do a lot of other things like group and clump and find centers of mass and figure out whether somebody's going to pass a test or not, which I guess is a yes, no, but you can actually almost figure out their grade based on how much sleep they got the night before. Anyway, point is that you can take input data, right, and put it through a neural network, and you can classify things. And that's what we're going to talk about today. All right. What are the 4 things we talked about at the end of last session? You need lots of data in order to train the neural network. And we'll talk about training second, because I want you to know how neural network works first. And for a neural network to work right first, you gotta already have it been trained. So we'll switch things around backwards, but you need a lot of collected data, and it has to be labeled, or it works best if it's labeled. So somebody's looked at all the pictures, right? And they have said, there's a cat in that one, there's a dog in that one, there's a horse in that one, there's an airplane in that one. So it's labeled. It's got its classification in with all of the data that comes in from the picture. Or in my audio example, did I say yes or did I say no, right? And I've got to have a bunch of people saying yes and no and and yep, and the affirmative, was I an affirmative or a negative? You got to have all that data, and you got to have it be labeled. All this data was a yes. All this data was a no. Then to make everything work, and we'll talk about this at the end, you need to develop a good cost function for that. And what's a cost function? It's to determine how wrong the system was if it made a mistake. We'll get to that in a bit. And then to do all the things necessary, you need a bunch of computing power. So that's your 4 biggies. For this is what Andy thinks he knows. Remember that, right? Okay, great. So I want to put some ideas together so that when I show you the actual implementation of this, you have an idea. So when we talk about the input layer, we talk about X's coming in, and other people might use different words, but I'm going to say all my data that's coming in, whether it's a vocal signal, whether it's an image, that's my X data. Okay. It's going to have this voltage at this time, et cetera. It's going to be this light level at this pixel. Let's just say it's black and white. And for this example, it is, right? If I wanted to put all of that data through a neural network, I would have to decide how many layers I'm using. Okay. So that input data here, X1 through X40, if in this example, you're going to see why it's 40 in a second. I'll leave that for now. Plus a bias, and we'll talk about that later when you're older as well. It's multiplied through a weighting matrix. Okay. And you'll see how that works in a second. But you multiply all of this data that comes in by a certain set of weights. How important is each of the pixels, et cetera. And then you get an answer. The answers are Z's in this. You get an answer at this neural network layer. Okay. So let's say that there's 50 neurons in this layer. You'd go from 1 to 50 and you put a bias on. We'll talk about that when you're older. Just a second. Okay. Then you're going to multiply all those through a weighting matrix, and you might get 25 answers and a bias. And then you put that through a weighting matrix, and that weighting matrix is going to give you your 4 answers out. Now, I'm going to show you an example where we're using a bunch of data that is pulled from census data, from like pictures of census forms that have been handwritten for a long time. So it's a whole bunch of handwritten numbers. Okay. But before we talk about that, let's just talk about that biasing for a second. Why don't I just use the data? Why do I have to add that B term? And I didn't know this really until preparing for this, but if you look at a line, right, there's a slope, which is M. X is where you are. This is the X axis. You can see the X there, right? You got a slope, and most people will understand this. And then you got this plus B. Well, why do we put the plus B in? If we don't have the B, if this is always 0, then this line will always go through the center. You can never bias it up or down. You can never move it. So what we want to be able to do is move all the data up and down at once. And that happens with a bias term, which is this last term over here. Okay. So let's talk about this for a second. This is the data that we're looking at, and this is from the MNIST data set. And it's just what I told you. It's a whole bunch of handwritten numbers. And you can see a bunch of these handwritten numbers over. There's a bunch of zeros. They all look different, and the ones look a little different. By the way, I'm surprised they didn't have a 1 with the little hat and the base on it. But I am happy that at least they had 1 7 that was crossed. And as an engineer, you cross your 7s, because then they can look like 2s, you know, and lots of other stuff. So, but you can see that there's and look at the 2s. You get the 2s that are the squiggle, and then you get the ones that loop around. So there's a whole bunch of numbers available. And there are lots of data sets like this, and you can have access to them if you want. Now, in this data set that I'm going to use, all of these numbers are captured in 20 by 20 pixel sets. So there's 20 pixels wide and 20 pixels tall. And there's some level of gray. So this is a grayscale, probably between 0 and 255, right? So you get 400 pixels per number. Does that make sense? Everybody, give me a good. So there's 400 pixels. Those are the features that we care about, okay? So how do you get a whole bunch of those into one place? Well, one way to do it is have each number get flattened out into 400 values and put that in a row, and then put another row below it and another row below it and another row below it. And that becomes a set of samples. So this one might be in row 0, that one might be in row 1, that one might be in row 2. So if I have 4,000 samples, I would end up with an array that's 4,000 rows, one row for each sample, and then 400 columns, one for each pixel for each of those samples. Does that make some sense? Is everybody with me? Oh my gosh, right through the RoboZone. That was good. That was a good move. I like that. Yeah, nice.
Yeah,
But so now I've captured all of my images here, and they're 400 pixels that describe them. Okay, good?
Good.
Great. So now what do we do? So if you think about it, now my X data coming in is 400 long, right? Now I want to multiply each of these plus my bias times a weighting matrix, okay? And then I will get answers that are some amount, okay? There's some value, okay? Then the next thing I want to do is figure out whether that neuron got activated or not. We're going to try to push it to 1 and push it to 0, or push it to 0. And then we're going to do the same thing again with weighting matrix 2. And then we're going to figure out answers and push them to 1 or 0. And then we're going to do the same thing from this layer 2, which got 25 answers in it, through a weighting matrix to my 10 outputs. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Good? Okay. So what you're going to see demonstrated is this is a weighting matrix. And in this case, it's got 50. If I've got 50 neurons and 400 pixels, there's a weight for each of those combinations. Pixel 1 with neuron 1, pixel 1 with neuron 2, pixel 1 with neuron 3. And so I'm going to take all of my 4,000 data sets, which are 400 wide, and I'm going to multiply them by this weighting matrix to get myself to answers in that first neuron set. Okay, just stick with me because we're gonna go through it step by step. You don't have to know this until your sophomore year of college, but it's good that you're seeing it now. This is how you multiply, or one way to multiply matrices together. Okay, notice 1 times 8, 2 times 10, 3 times 12. That's the first row in the second column, gets me 64. If you want to check the math, go ahead. 1 times 7, 2 times 9, 3 times 11. If I do that, that gets me 58. So I get this number based on adding the multiplication of each of these rows, each of these values in this row with each of these values in this column. You add them all up and that's your answer. First row, second column goes to there. First row, second answer. If I want to do the same thing down here, I'd take this row and multiply it by this row or this column, and I'd get an answer there. And I could take this row and multiply it by that column, I get an answer there. So I've got a 2 row by 3 column matrix and a 3 row by 2 column matrix, and I get a 2 row by 2 column matrix. So notice my 2 row by 2 by 3 multiplied by 3 by 2 gets me a 2 by 2. So you just take these middle things, which have to be equal, and throw them out. And you get your answer. You get 2 by 2 as your resultant. You'll see why that's important in a second. By the way, in order to do that in C, I have to have nested for loops. So I'm going to say, all right, go to row 1, column 1, take that number, go to row 1, column 1 in the other one, multiply those two together. And I'm going to keep doing that for all of the rows and all of the columns. So I'm going to keep doing multiplication and addition, and then I'll get my answer, which is my result. So actually the math is not that hard. It's just multiplying and then adding. You just have to put that in for loops in order to get through the whole matrix and get every one of those answers that you want. Now, in MATLAB, it's actually quite easy to do this. You simply take matrices that you set up and multiply them together, and it does it for you, as long as the columns in one equals the rows in the other. So let's just take a look at this for a second. Here's my X data that's coming in. Remember, that's the input data. And remember, there's 400 pixels in each one plus a bias, right? Plus a bias. So I got 4,000 samples, 401 pixels plus a bias. Well, 400 pixels plus a bias, right? Take a look over here. My weighting matrix, what's the size of that? 401 by 50. Now, it's actually 50 by 401, but it turns out you can transpose these things and you get the two things that need to be equal to match up. So when I put in my inputs and I multiply by that weighting matrix, remember what my Z's were? My Z's were the answer, right? So I get this result, and that's now 4,000 samples and 50 neurons for each sample. It's all the neuron results for each sample. Sorry, I keep hitting the button. I'm getting excited. Here we go. And then you do the same thing. Now I've got 4,000 samples and 50 results. And I take that, I add a bias. Now that's 51, because you had 50 neurons. Now you add one more, right, for your bias. I got 5,000 by 51, and I can make this 51 by 25. So how many results do I get out of that? 25. So I get an output that's 4,000 samples and all 25 neurons in the third layer, which was my second hidden layer in that picture, right? And then I do it all again. I add a bias. So now I've got 26 because I got all those neurons plus my bias. I multiply by a 26 by 10. How many outputs can I possibly have, John? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 10 total ones. And that gives me 4,000 samples and 10 possible outcomes. Okay. Then I figure out which one is the highest, and that tells me what my number was. How cool is that? It's super cool. You don't have to tell me how cool it is, John. I already know, okay? Because it's neat.
It's hurting my brain.
No, but this, it's just to say, so now this is called forward propagation. I'm taking my data, I'm multiplying by weighting matrices, I'm getting answers, I'm multiplying by weighting matrices, I'm getting answers in these hidden layers of neurons, and then I get my output, okay? Now, the one thing I haven't told you about yet, and it shows up in the demo, is that you can just have the answers be the answers. But what you really want is you want one answer to be way bigger than all the other 10, right? You don't want it to be unclear. You're trying to make your weighting matrices give you a really good, crisp answer. And one way you do that is in the hidden layers. Remember I said Z was the answer? But then I had a number or a letter right next to it that was A. And I know that I should have used a different idea than A, but it's called the activation. And you can use an algorithm. It's not an algorithm, an equation. An equation, that's what it is. Must be late in the day. Yeah, it's 4:26. So you can use an equation to push your answer either 1 and 0. And the equation that we used in our class was called the Zygmunt function. And it's this one where it's 1 over 1 plus e to the negative x. The only thing that's really weird about that is the e. The rest of it's just math, right? It's an easy function to make. And what it says is, if I give you a 5, that's a 1. If I give you anything over 5, that's a 1. You have activated. And there's under 5. So you can have any value way out, and it'll get turned into a 1, right? Or a 0. If I give you this negative number, that's going to turn into a 0, right? -5, -10, -100. We're pushing that to 0, right? But there's this little thin space where it can be, maybe it's 0, maybe it's 1, but we're not quite sure. And so that's why we have to train over and over again, is because we want to push those neurons to say, yep, you either got activated or you didn't, okay? So we use the sigmoid function to turn activation, to make sure whether something's activated or not. So now let's come back through. We propagate all the way through. We do all of these weight matrices. And then in your output layer, you're going to get 1s and 0s. you're going to get, was this a 0? No. If it wasn't a 0, then that means it was another number, right? And so you can do a one versus many organization of your outputs, or what we ended up doing in our class is we figured out which one was the highest probability, which one got activated at the highest level by that series of multiplications and zigomoids, okay? And I'll show you that in a second. So here's the demonstration. Now I'm doing this in MATLAB, but like I said, you could do this in C. You could do this in Python because you can multiply matrices, and that's all we're doing, okay? Now, what's first thing I do? And this is, again, this is from Youngmei Park's class. So I'm just using MATLAB to load the data. So I'm running this section, and this is MATLAB. And the only reason I'm using it is so much easier to do matrix multiplication in this. And so now I've got this data set that's in here. And if I want to look at it, it's over here in my data set section. And I can take a look, and you can see I've got 4,000 samples here, right? And that's for my training. Turns out, by the way, we're just going to, whoops, sorry, that's how many samples is there. And but we have the data in place. Now, if we come down here, what I want to do is just show you some of the samples. So I display them, and notice, here's what they look like. Those are 20 by 20 images of numbers, just like we've been thinking about. So this is what each of my 4,000 samples is going to be. Okay, so now I want to load the weighting matrices. So I do that, I run this section, and we get now a bunch of weights that we'll be able to see in a second. And down here, what I want to do now is do the multiplication that gets me propagated through in the forward direction. So I take my number of samples and I put a bunch of ones in here. So I've got 4,000 samples. I want to put a bias on each one of them. So I make 4,000 ones and I jam it onto my X training data. That's my X values. Okay. Notice, by the way, you see a bunch of zeros here, but that's because in the top corner of almost all of the writings, there's black, which is 0. So it doesn't mean there's nothing there. But after I do this with my bias, I end up with a set of ones at the beginning. That's my bias. Okay. So now that was my input layer. I put the bias on, and the next thing I want to do is multiply that input layer by the weights in weight 1. So remember I said I have a pre-populated weight thing already. It's already been trained. Okay. Notice in there, you see all those numbers? All those numbers are the weights that are going to be associated with all those multiplications that we have to do from the input data to get to the answers in the first neuron layer. Okay, sticking with me a little bit. Okay, so I've got, and what is this? This is 401 by 50. So I transpose it so that it's 401 by 50. I'm sorry, it's 50 by 401 here, but 401 by 50 is what I need. And then I multiply that together and I get my answers for my layer 2. That's my Z's. So I get all these answers, but notice they're not zeros or ones. They're not even between 0 and 1. There's lots of different numbers in there. So then I do a zigomoid and I get activations. So now I've taken all those and I've pushed them closer to 0 and 1. Okay. And then what do I have to do at the end of every neuron activation? I have to put my bias on. So I put another set of bias values on. That's 50 long. I'm sorry, yeah, that's 4,000 long, right? But now onto the layer 2 activations. And then I do the same thing again. Now I take my weighting matrix 2, which is 51 by 25, and I multiply it through by the activations that came out of layer 2, right? That first hidden layer. Input was layer 1, layer 2 was the first hidden layer, and I get answers for layer 3. Z3, and there they are. And again, they're not between 0 and 1. So we do a zigomoid and we do 0 and 1, and then we stick a bias neuron on that layer. And so then we get to our final, it's a 2-layer network, but even that is considered deep, by the way. So, and you'll see why in a second. Then I get my weighting matrix 3, I multiply it by the activations from layer 3, and then I get the answers for layer 4. And then I can turn that into an activation by doing the zigomoid again. And I called that prediction because now I'm predicting what value I see. Okay. So if I run this section, I had to do some accuracy for the lab, but what I really want to do is come down to the end here. So at the end, what you want to do is take, this is why there's training data and test data. you want to test on data that you didn't train on, because you're going to get the training data right because you trained on it, right? But the test data is brand new data that this weighting matrix set has never seen. And notice we picked 12 of the results. I'm sorry, 16 of the results here. And these are the numbers that it predicted, and they're all right. So we take that, we forward propagate, and it figured out, just without me telling it, giving it anything but these weighting matrices, right? The engineer didn't have to be smart. I just got the weighting matrices and gave it to the thing, and it got the right answers. So let's land the plane on the second part of this, okay? So that's, remember, lots of data labeled correctly, good cost function and computing power. Now let's do those last two, okay? The last two are, how do we pick the weights? Or how do we get the weights to be right? Well, if you got good labeled data, you need a good cost function. And then the one piece of math that you have to understand how we got here is differentiating, but I'm going to tell you about that. So don't worry. Okay, so let's do this thing. What does labeling looks like? By the way, this is the labeled data. This is the Y data, the answers for that data set that I just said. So there's about 400 zeros and ones. So this is right where the ones become the twos, right? So this is my labeled set. And it's, remember, for training, how many samples did I have at the beginning? 4,000, right? And this is 4,000 by 1 because there's only one right answer, right? It is a 2. It is a 1. It is a 9, okay? So for each of those samples, I have an answer. What was the number? It's right here. It's in this array, okay? Okay. So now how do you tell how wrong you were? This is called logistic.
My wife can tell you.
Oh, no, for sure. And you might actually use this with her later. I like this idea. If I guessed 0, I'm sorry, if the answer, remember, Y is the answer. X is the inputs. We have these Z's and these A's in the middle, and we get Y as the answer, okay? If the actual answer, the real answer is 1, and I guess 0, how wrong am I, John?
Pretty wrong.
I'm almost infinitely wrong, like super wrong, like inconceivable wrong, right? I mean, I was trying to do
Right,
French,
Henry?
but the French wouldn't come, Pete, sorry. Okay, if I guess 0, I'm sorry, if the answer is 0 and I guess 1, was it that thing? I'm 100% wrong. And then as I get closer to 0, I get to be 0% wrong. That's a cost function, okay? So this is a logistic regression, and it turns out that this is the hard math that shows it, but it's really neat because you see this 1 minus Y? If I guessed 1, what's 1 minus Y, John? What's 1 minus 1? 0, exactly. And if I guess 0, what's Y? 0. So this basically adds these two things together, and you get something like this. Now, why is that a really cool function? We really like this. We've added these two things together. It gives me the cost of either 1 or 0. I just add them together, okay? I don't care about this part. I just care about the top part, and I get a parabola. Now, why are parabolas neat? So here's calculus 1 for non-majors. At any point on this curve, I can figure out exactly what the slope of the line is at this curve. All right, that's called the derivative, okay? Now, why is there a happy face down here, John? Because if this is the error, this is how wrong I am. Wrongness keeps going up by the edges, right? So the least wrong I can be is at the bottom of that thing. And if I try to draw a line there, the derivative is straight line. It's 0. There's no slope either direction. And here I've got positive slope, and here I've got negative slope. Here's the key to training a neural network. So what you can do is go through each of those weights and each of those neurons, each part of the system, and figure out how much each of those parts contributed to your wrongness by doing what's called a partial differential equation based on just those variables, the part that you're looking for, which means you can, once you find out you're wrong, you can back propagate through the system all the way and figure out, hey, at this point, I was this wrong. So what do I need to do to that weight? I need to push it in this direction. I'm going to be more right. And if I'm on the other side, I've got a negative slope. So I'm going to push it this direction. By the way, there ends up being a negative. So if you've got a positive slope, you go in the negative direction. You got a negative slope, you go in a positive direction. Okay. And you can program this because all it is just matrix multiplication. Once you get the cost function, and really the derivative of that is based on this thing, which is P and 1 minus P, which is your prediction. And so the point is that gets you a delta for each of your weights. For each of your weights in your matrix, you end up with a delta. And again, notice something minus Y times that thing that was right there. Okay, so they took the derivative of that cost function for you, and it turns out that the math is not that hard. It's a subtraction, it's a multiplication, and it's another subtraction. Okay, trust me on this one. I'm not going into the math. All right, I'm just not doing it. And the same. So this is my how do I move all the weights in layer 4? Okay, from layer 4 to 3. How do I figure that out from layer 3 to layer 2? Remember, each of these can be a whole matrix. This isn't just one number. So this is happening over and over again. And remember, you'd be required to use nested for loops if you were doing this in something other than MATLAB. But it's just easier to write like this. And we've only got so much time, right? So you back propagate through, you move all the weights, and then you calculate the slope of the thing, and then you can move the weight based on your delta. Okay, so then you move each weight, and then the way that you move it is based on a learning distance. So remember, in this, there's a certain step size between here and here, and here and here, and here and here. That's your learning speed, or alpha, okay? And that's just a number, right? So you take where you calculate your slope, you figure out times alpha where that needs to be next, and then you update all of your weights. And then you repeat step 3. So you forward propagate, see if you got the right answer. If you didn't get the right answer, guess what you do? You back propagate again. And you keep moving those weights until most of them are down here at the bottom. They're in the happy spot of that error curve. And then you've got a model. Now think about that. What does an engineer have to do to make a model? They got to learn a bunch of math. They got to apply it. They've got to understand a system, get a sense for how it behaves and all of that sort of stuff. What do I have to do with this? I just have to forward propagate, boom, like this, figure out if I was wrong, and then back propagate and update my weights. And the weighting matrices become the model, and they become very, very good. In fact, with AlexNet, I guess in 2012, it's now better at recognizing pictures than humans are. It's more accurate, I should say. When looking for a certain thing in a picture, it can pick it out better than a human can.
Chinese are really good.
I'll tell you. So that's neural networks. I can't show you an example of that because we ended up using some built-in tools from MATLAB rather than doing all the back propagation ourselves. But if you dig into this, well, this is fundamentally changing the world around you right now. So I like the Facebook example. We've been talking about images and numbers, but they've got a model for me in their back office somewhere. And every time I like something and every time I interact with something, that's labeling data for them. I just labeled my own data by saying, oh, I like that. And oh, I'm talking to that person. And it figures out then as it's trying to fill up my news feed or whatever that's called, right? Because I'm elderly, you can see I'm new to Facebook enough, right? I've only been using it for 10 years. Anyway, the next thing it shows me is based on its model of me. Okay, when you talk to, well, that's the most important one. I don't want to go into too much more because that one I think is fascinating. And I don't know how many dimensions that is. Remember, there were 400 different pixels that it looked at for those handwritten numbers. I don't know how many important features it's looking at for me to figure out what I want to see next. And that is why this is so interesting. And if you want to dig into the math, now you have some guideposts, right? Because it's not all done the same way. And it's not all done for there's convolutional neural networks and deep neural networks and they can be used for different activities. But now you've at least got some language that when you go out and look and somebody says, oh, I'm training my neural network. Now you know what they're doing. They're figuring out how wrong they were over and over and over again and coming up with a model in the space between the neurons. Oof, that's exciting. And they're doing this everywhere in our economy right now. It's helping voice recognition. It's helping image recognition. It's figuring out what to show you next on Facebook. It's on Netflix. How do you think that it tells you, that it figures out they've got a model of me in there too? What do I want to watch next? Right?
Yep.
And this is the core ideas around it. So I hope that was interesting enough. And I thought about splitting it up into just forward propagation and back propagation, but I said, no, let's land the plane today. And I think we did.
So this is the kind of thing, a lot of times, it depends how your mind works. You got to go over a couple times, 3 or 4 times.
And there's
to be
not
able
just
to,
one way to do it.
Right.
That's the big
Yeah.
thing. You
But-
want to then figure out all the ways to do it.
But to figure out numbers, but then you can take it to another level. And say for auto drive, think about all the things they have to look at for auto drive, how many calculations are in there. And then every time you think about that, throw in another something else,
Sure.
right? Another attribute, another variable, however you want to look at it. And then you see how difficult it is. It isn't just the stripes on the road or the barrels on the road. Or
Is there a
person walking
bicycle? Yeah.
down the road, or a bicycle on the road, or a bird, right?
Well,
What is a bird a barrel,
I-
right?
I-
I mean, there's so many things.
I tell you,
to
John,
look at.
I was in Nigeria talking about autonomous vehicles, and also in Uganda, but this particular story happened in Nigeria. I said, what happens when the first autonomous vehicle runs into its first elephant with its forward-facing camera? Because they're not designing cars in Africa right now. They should be, they could be, they're smart enough to do it, right? But they just aren't because of all
It's
sorts
not a
of
human,
historical.
It's not a cone.
And
So-
you don't show cars elephants when you're in Germany designing a car or in Japan. They just don't show them elephants. So what's it going to do, right? And the other interesting thing to know is that the training happens all at once at the beginning for those kinds of systems, and you lock in those algorithms there. But then, can you hack that system? Because they resell those cars in Africa, right? I mean, top selling car in Africa is a Toyota, right? It's everywhere. Okay, there's Toyotas all over the place. Lots of them have forward-facing cameras. Can you then hack that and retrain the algorithm to see potholes, to see elephants, to see whatever?
Or whatever it is, a lion.
Or
right?
what if you've only trained your algorithm on white people in front of your vehicle? And you just haven't trained the algorithm on what people of color look like from your camera, right? What if that's true? I mean, that can be a
I've
problem.
already had issues on that with facial recognition in multiple.
And figuring out skin cancer, hey, by the way, you can use this. You can look at a bunch of skin samples and as long as they're labeled, right? So you say, well, this one turned into skin cancer, this one didn't. You can do the same process and you get a neural network for detecting skin cancer.
Yeah, well, one of the things for Watson Health
Yeah.
was they were training it for triage. Someone comes in, boom, 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 boom. It takes a bunch of tests. It does things, this, right? And it'll give you a percentage of what it is, just like on Jeopardy, when it went in there, it's
Yeah.
a 70% chance that that's
So
the
that's
right
the
answer,
answer, yeah.
90% chance, right? That's what it did. It just did a whole bunch of
Right.
quick functions.
Well, I mean, I
Talk
could go
about
on and on about this. I know that Pete got food delivered, but I don't know, what questions do you have? How do you want us to land the plane on this?
I think you did land the plane for me. I thought I will watch this again, maybe twice, just to comprehend it.
But you don't have to know the math. You just have to know that this stuff is sloshing back and forth. And if you can just remember, anybody, not you, but anybody can remember that the model is in those weighting matrices, that is a huge step forward in understanding these things.
I am realizing this application, how many of this application is in my house alone?
Oh my gosh, Alexa?
I have the Nest camera on the front of the house. It's built into that. I have a camera in the back, protecting the backyard. It's built into that. It's built into, I have Google throughout my house. I shouldn't
There
say
you
that
go.
out there, but yeah. So it's built in all the speakers. It's Alexa, it's built into Alexa. It's built into your phone. It's built into the websites that you're in. It's built onto your Instagram, I mean, everything.
Well, and you know, do you know the story? And this is a little touchy of a subject, but the AI within CVS or Walgreens, or because they all have an AI engine in the back of their stuff too, that's looking at your swiper card and what you just bought. It sometimes starts to send people
Right.
like things about well, no, it starts to send you things about being pregnant when it knows that you're pregnant and you don't yet, because of the way that you're behaving. And same thing is true with these. I've got an app here that's figuring out my heart rate and whatever.
Yeah.
That these can sometimes, because all that data gets aggregated, right? And if they sell it to somebody, which not everybody does, but then all of a sudden you start getting, you know, heart disease pills, ads, when you don't even know you got it, you know?
Yeah, is it good or is it bad? Is it personal information? There's so many things.
This is a brave new world, man.
We still have to go through and stuff like that. Is Alexa listening to you when it's off? Of course it is.
It's always listening. Does it trigger? Does it get triggered?
That's the right term there.
Right?
Yeah. So yeah, it's a
My recommendation, John, to everyone that's listening or watching this is, and we never do this, well, I try the best I can, is read the EULA, the user license agreement. When you start doing things, when you start creating accounts, when you log on to Facebook, everything, read the EULA, and you will find out a lot of information about what they're collecting just by reading that. And sometimes people should read things before they do things.
I think somebody said that if you read everyone you were presented with, like it would be a third of your life.
Yes.
And a third of your life is spent sleeping. So half of your waking life would be like reading user
Well, there should be
agreements.
For the end user license agreement.
Yeah.
Right, there should be a little box that says blah 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 in shortened form. You know,
Well,
but
maybe one of the days.
I want to say one other thing before we go, because this is important. And I said it at the beginning of the first one, so I'll say it at the end of the last one. You still have to know the math. Why? Because we're still bad at figuring out what the actual neural network learned. We just don't know, because it doesn't say it. All those numbers in that array don't say, oh, I'm looking for a yellow box to shoot, you know, the target through, to shoot the ball through. So you have to learn the math to figure out if your robot has learned something plausible, right? Rather than something else, so that you can keep it safe if it learned the wrong thing, but in a little tiny corner case, right? So you still have to know the math, learn your differential equations, go to calculus, all of that stuff. Okay, that's my public service announcement.
each of
Get
these
sleep before you go to math class is basically
Man,
what
do
you're
that.
saying.
Do that for sure.